both from the University of Reading. He is active in international professional bodies, including being chairman of Safety Study Committee, D1. Materials and emerging test techniques, and a member of editor board of IEEE editorial insulation magazine. He is a visiting senior research fellow at the University of Southampton. So actually, I want to do like a brief background introduction. Why today we host this event? We know cable is a niche market. There's in terms of discipline and engineers involved. But in the last 10 to 20 years in our country, we try to push net zero. So we promote building more renewables, especially offshore wind. We see offshore wind industry as our national strategy. When we talk about offshore wind, most people put their attention on the power plant side, which is turbine. Of course, we need a good turbine which can stand in the sea condition. But that's not enough. We also need substation equipment and to suit, which can convert, especially long way offshore. We need a DC-AC converter and an inverter other side. So converter, inverter, both sides, offshore, onshore. So cable is one of the enablers. The importance is just as important as a WTG, the turbine and wind turbine generator. It's just like that, because I've been in different committees with National Grid and Ofgem, and so apparently cable is in a big shortage, the whole supply chain of cable. If you have like yourself or anybody you know or your children or whoever, they are studying engineering, pick up cable. It's most important. That's not a joke. I know in the company I work, I was director in McDonald's. For many years, one of my things is national excellence is finding targets. Another thing is to promote leading edge technologies. So cable is one of them. So without any further ado, I know assignment.
Okay, so good evening, and thank you so much for coming. Hopefully this will be informative and a little bit of fun. I do have some samples down here at the front. I didn't quite know what the room layout was going to be, and they're quite heavy, so they're not going to be so easy to pass around. But I can show you, and then at the end, if you want to come down and take a closer look, then please feel free. So just to give a very quick, I didn't know what the diversity of the background of people were going to be here. So at the beginning, I have a few very quick, simple slides to introduce cables for those who aren't 100% familiar. And also, the cables we use today, on one hand, are very similar to ones from 100 years ago, but then again, they're also very different. So I just want to show some examples. I'm then going to go through some basics of forensics analysis. And if anybody who's ever watched, CSI on the TV or any kind of murder mystery program, then some of this should all be common sense. However, most of the time, most of the investigations I get involved in, that common sense generally seems to go out the window on many occasions. So this is taken from a course I give, so there's some very simple basics for rules for what to do if you ever get involved in a murder, or a forensic investigation of a cable, or any other power asset for that matter. It's all transferable across any kind of data investigation. We'll talk a little bit about some of the techniques that get applied. And again, if you've ever been involved in any kind of material analysis, or you see them on the TV with these murder mysteries, they're all the same kind of chemical, analytical, physical techniques. And then to pull it all together, I have a little case study at the end to show you, how some of these things are applied, And it's a medium voltage example, but it could equally apply to high voltage or HVDC. It's the methodology and the systematic approach which is important. So very quickly, just to introduce Doble to anybody who doesn't know it, or anybody who thought they did know it. Doble's been around for over 100 years. We had our 100th birthday 2 years ago. And for a very long time, we're a family-owned company. Until 2007, when Doble, the family sold to a technology company called ESCO. They're an investment company in the US, in sort of the high-tech, high-niche. They do a lot in aerospace, with the military, but also they have a utility service group of which Doble is part. And I joined almost 8 years ago, and a month after I joined, we bought this company called Morgan Schaefer, which is kind of the Rolls-Royce of dissolved gas analyzers for transformer monitoring. And then since then, we bought all these other companies. So our portfolio of what we do has changed enormously. So if you think you knew what Doble used to do, think again, because actually in 8 years we've changed enormously. To the extent that when I joined, we were 300 people. So as I stand here today, 8 years later, we're now 800. And that's all through acquisitions, but also through diversifying what we do by bringing new companies into the group. And internally, I was talking to somebody beforehand and saying basically, we make specialist high voltage test equipment. So things are going in testing transformers, testing circuit breakers, testing GIS. We also have online monitoring solutions, and from an asset management point of view, online monitoring is really important these days. So transformers, cables, GIS, circuit breakers. If it's inside the boundary of a substation, we pretty much can test it or monitor it. And I work in the professional services part of the company. We have a service team of about 30 people based here in the UK. We work with the utilities, power generators, heavy industry, offshore wind industry as well. We have guys who are qualified to go offshore and do testing. But we also get involved in training, get involved in going to factories to do audits on transformer factories, cable factories, manufacturing inspections, FAT witnessing, factory inspections, test witnessing, asset management consultancy. That's all kind of in the services. That's all the fun stuff, because most of those projects are bespoke. So no two projects are ever the same, so it doesn't get boring. I think I just covered this. So online testing, offline testing, consultancy, witnessing. We have a team based in Italy who get involved in a lot of cable commissioning. That's the tech part of the business that span out of the University of Columbia some years ago. And they travel the world, commissioning cable circuits. And then forensics, failure investigations is also part of services, and clearly that's what I'm here to talk to you guys about today. So it's a fun time to be in the power industry in general. Decarbonisation, expansion of power networks, drive to electrification of all sorts of processes. And as I was saying just now, doesn't matter if it's cables or transformers, lead times on assets is getting longer and longer and harder to get things quickly. And from a cable point of view, yes, onshore and offshore wind, huge increase in demand. So that's for the array cables within the wind farm, but then also the export cables, be they AC or DC from the offshore substations back to shore. Solar farms, also lots of medium voltage cable going into solar farms. HVDC was mentioned earlier. I've listed, these are just the existing links from the UK as I stand here today, in chronological order. So I for one, the Connector to France was the first one. Green Link commissioned in theory in January. I'm not sure whether it's actually commercial yet. They went through commissioning a few months back. And on that list, we've got the world's longest link, Viking, 700 kilometers, UK to Denmark. We've got the world's highest voltage nanotechnology cable, which is NEMO, which puts nanoparticles into the insulation compound to improve its characteristics. There's only 2 of those in the world, one in Japan, one in the UK. And not on here, because it's technically not classed as an interconnector, it's an intra-connector. So from Scotland to England, the Western Bootstrap is the world's highest voltage PPL link. So within the UK, we have 3 global leading HVDC links. Other drivers for more use of cable, storm hardening. Climate change, you can blame for this to some extent as well, but trees come down, takes down overhead lines. If you're in America, hurricanes, tornadoes, take lines down. So there's a drive in some parts of the world to get rid of the overhead lines, put it underground, because it's more resilient when these storms come through. Not so much of an issue in the UK, but fire resilience as well. Look what happened in LA recently. LA didn't suffer so badly in LA because most of it was already underground. The communities outside of LA suffered enormously because if everything's on a pole, the pole's burned down, it takes you ages to get your grid back. So undergrounding in areas where there could be fires is also a driver for more and more use of cable. And then we always have the contentious one of visual amenity at the very end as well. People don't like to look at overhead lines, and in some parts, and National Grid is doing this in a few places in the UK, undergrounding overhead lines in national parks to improve the landscape. So what do I mean by a cable? And a cable is more than just this thing. It's more than just the cable. You need things to connect to the cable at either end. So depending on the voltage class, you might have an outdoor termination or a GIS termination where it plugs into a GIS substation. You have some, we call them joints, the Americans call them splices, but that's the thing that connects the individual lengths of cable together. And we'll be looking at an example of a joint failure later on. And if it's medium voltage, you probably have a plug-in connector, so offshore wind farms, either at 33 or 66 kV, usually a plug-in connector, which also means it's easy to disconnect, easy-ish to disconnect, if you need to do testing. And of course, this is an AC system, so we have all of this 3 times over, 3 different phases. And here's a few examples of different types of cable. They all kind of look pretty similar. They've all got a conductor in the middle, they've all got some insulation around them, and then there's some kind of containment on the outside. And that hasn't changed ever since the late 1800s, basically. On the left-hand side of the screen, as you look at it, are the modern XLP kind of cables, like this. And then on the right, we've got older style cables either with oil or mass impregnant. This is a PILC cable, so this is wrapped in paper in sort of a greasy wax. That was used from the early 1900s up until the 60s. There's still some of it in operation. This is a typical oil-filled cable that was the foundation of the national grid in the late 60s, early 70s. Lots of that still in the UK as well, still operating fine. Unusual one in the bottom corner, this is a gas compression cable. There was 2 of these in the UK when I started in the business kind of in the late 90s. They disappeared very quickly after that. Great until it springs a gas leak. Then trying to keep the air pressure up inside is very hard. So a lot of variety, but generally they all come down to this. Piece of metal in the middle to carry the current, some kind of insulation around it, and then some kind of containment either to keep the oil in, or in the case of these XLP cables, to keep the water out. And then some kind of protection on the outside of the cable oversheet. And that's normally, these days, it's normally polythene. If you come down and feel these afterwards, you can actually feel that the materials on the outside of these 2 are different. This is a hard material. And if you're going to pull this into a trench, into a tunnel, you need to protect this. This is what protects the cable during transportation. and during the installation process. Once it's in the ground, in theory, it's safe. Until somebody with a JCB or pickaxe comes along and attacks it. And that's what this is there for. That's what it's here to try and prevent. If it's a subsea cable, and so I'm not going to pass this around, this is only a 66 kV cable. So if you imagine scaling that up, this is I think 132, so a little bit bigger, so you have 3 of these in the bundle. And if it's a 400 kV, this gets very, very big. But this, this has steel armor wire on the outside. Again, this is going to get chucked in the bottom of the ocean. It has to protect it against movement on the seabed, rocks, and people with anchors. And this is becoming, strategically, driving down in the car earlier, they were talking about strategic industries, talking about the British Steel and taking over the site from China, national security. They were also, Radio 4 was also at Hinkley Point C tonight, talking about energy security. They were talking about the number of interconnectors connecting the UK to France. And the implication, although they didn't say it explicitly, was this is a national threat. There was the Nord Stream gas pipeline that got cut in the Baltic by foreign actors. I think 9% was the quote when they were live on air tonight. 9% of the UK's electricity was coming in from the continent. If somebody wants to go and cut one of these cables, they're all marked on ship maps, to try and stop people hitting them with anchors by accident. But it also tells people exactly where they are, if they want to go and deliberately take it out. So I'm going to talk a little bit about how you joint cables very quickly, because we're going to come back to this with the case study that we're going to go through. So, I said you've got 2 cables, and you have to find a way of jointing them. So this is kind of generic, but it kind of gets the point over. So here's the guy in a hole in the road, getting on with the job. So the first thing you're going to do is going to take your cable. You're obviously going to cut it to make a nice clean end, and then you're going to start to peel back these outer layers so that you can start the jointing process. And you can see here, so there's one cable here. This is the connector in the middle. So the insulation, the white bit's been exposed, then there's the outer semicon, and the metallic part on the outside. There's tools for doing this to make nice clean surfaces. What you don't want to find is this. These are real examples. This should be a nice smooth white surface and a nice sharp transition between the insulation and the semicon. I was talking to somebody in the freshman break beforehand, saying during a factory acceptance test at a well-known cable manufacturer, this was only a 66 kV cable. Actually, it's the one that went into this. So this was done in the laboratory at a cable factory by people who are doing this every single day, actually really, really skilled at their job. All of this stuff shouldn't be there. This broke down during the factory acceptance test. Really poor workmanship, shouldn't happen, but it does. Then you're going to join the conductors together. There are different ways of doing this. This is a shear bolt connector. So you have the 2 pieces of conductor, you have the connector that goes over the top. You crank the bolts up and they shear off at a certain force. It takes some of the old days it used to do with a torque wrench, and it relied on the joint of being very skilled and following the instructions. Now he just ratchets it up, gets the right tension, and the bolt shears itself off. The example you'll see in the case study later is a crimped connector. So you put the ferrule over the 2 conductors, and then you use a hydraulic press to squeeze it all together to make the electrical connection. And then once you've got that in, you're going to start to reinstate the various different layers. This is quite a nice picture, because actually you can see this is part of the joint body that's going to go back. over the joint, because what you have to do is when you cut the connectors or cut the cable in the first place, you separate them, you slide the rest of the joint on, join the conductors, and you can slide the joint body back into place, and then let it compress down. And so you're then going to reinstate all the various layers to make the joint afterwards. And since we're going to be talking about a cold shrink joint, here's an example. So this is what it looks like before it's installed. So it's made of silicone rubber. It's basically a big tube, and it sits on this white expanded spiral. So it's going to end up this big, and when it's supplied from the joint manufacturer, kind of this big, held on this spiral. You slide it over the cable, and then when you want to take it off or compress it down, this bit that sticks out the end is actually connected to the far end. And as you pull it, the spring basically just pulls through, and the whole thing shrinks down and snaps into place. It's quite clever. That's why it's called cold shrink, because they don't actually have to do anything with it. The alternative technology is called heat shrink. Both make good joints if they're made properly. And there are utilities and operators out there who will swear that this is better than heat shrink, and I will find an equal number who will swear that heat shrink is better than this. It's all based on people's experience that they've had in the past. They've had a bad experience, it's very hard to convince them to go back to a technology. So this is from the IEEE magazine. I'm on the editorial board for it from years ago, way before I was involved. But like this is a jointing process. And here's the guy with the oxyacetylene torch, in these days, welding the conductors together. And it wasn't that long ago that we were still using welding on some big cables, even in this country. So he's welding them. This guy is then filling the joint, around the joint, filling it with bitumen. We still do this on some transformer terminations, even today. Cable boxes on transformers are filled with bitumen. Of course, when I put this up, I always ask the question, what has changed in this photo? Guesses? Health and safety.
Oh, yeah.
Where's his hat? Where's his gloves? Where's his glasses? This guy's handling molten bitumen, this guy's welding. But it's recognizable, even though this picture, I don't know when in theory it was drawn, probably well over 100 years ago. But it hasn't really changed. It's still a manual process. It still needs skilled workers. Jointing is a very skilled job. So, introduction to forensics. I'm going to go through this reasonably quickly. As I said, most of you who've ever watched any kind of cops and robbers shows with a dead body on the floor will understand this. So, fundamentally, the question we're trying to answer is, why did it go bang? Why did it fail? Why is my cable termination all over the substation? Why aren't I transmitting power anymore? Why have I created a small speed bump in a road with a big cable and it's gone pop? Unfortunately, there's a lot of energy in these faults. If you want to have a look, this is a pretty hefty copper conductor, and you can see what the fault current has done to that. That's just been eroded in the time before the protection stopped the fault. This is from a high-pressure fluid-filled cable from America. And I gave a course over there, and one of the guys worked for one of the maintenance companies on these. He said, "Oh, I've got an example at home. Do you like me to bring it in tomorrow?" I had to check my luggage in because I couldn't take that in hand luggage. Offensive weapon. But a lot of the energy often destroys a lot of the evidence. So a lot of the time you're trying to work out, what evidence do I have? What's the hypothesis for why it failed? And does the evidence support that? And then you sometimes have to iterate And sometimes you end up with okay, it's 80% likely to be A, 15% likely to be B, 5% likely to be C. It's not very often you get a 100%. It's absolutely that. There's lots of standard methodologies for doing failure investigations, and the list would go on and on and on from here. The 5 whys, fishbone diagrams, failure modes effect analysis is normally, overkill for most investigations. Pareto analysis is the fancy name for the 80-20 rule. I'm going to look at a couple now just to kind of give you an idea of how they work. 5 whys. So you define the problem. So picture number 1 at the top, nice little cartoon. Why did the machine stop? Well, it's tripped out. The key to the 5 whys analysis, anybody who's got kids, grandkids, great-grandkids, think like a 3-year-old. Just keep asking why. So why did it trip out? There was insufficient oil on the shaft. Why was it insufficient? The oil pump was inefficient. Why was the pump inefficient? The pump drive shaft was worn. Why was the pump drive shaft worn? Can you imagine the little kids doing this? Why? The oil filter was blocked. And usually, 9 times out of 10 in these kind of investigations, because you could say why again now, why was the oil filter blocked? Because somebody hadn't done the maintenance. Half the time, it comes back to somebody not following the maintenance procedure, not doing what they were supposed to do. And we'll come back to this again in the case study. So, another quick example, why won't my vehicle start? Battery's dead. Why is my battery dead? The alternator's not functioning. Why isn't it functioning? Well, the belt's broken. Why is the belt broken? Well, I didn't do the maintenance when I was supposed to do. We didn't follow the recommended maintenance routine. So you get the idea. It's pretty simple. It's actually pretty powerful, especially if you do it with like 2 or 3 people. You just keep poking at the problem, just drilling down and down and down. A kind of different way of doing it is these Ishikawa diagrams, obviously named after Mr. Ishikawa. But it's also called a fishbone diagram because it's meant to represent the spine of the fish and the ribs coming off. And it's kind of a way of doing an organised brainstorming. So you break the problem down into different areas. The equipment, the process, could be the manufacturing process, the jointing process, the people involved, the management, the environment, materials. These can be, as I say, you can do it really just with a simple brainstorming exercise, but it's a way of structuring it, and it's also quite a good way of sometimes collaborating with colleagues, because I can sketch it out, normally maybe as a brainstorming thing rather than strictly following this kind of laying out structure. But I can then send it to somebody, go, do you think I've missed anything? Look over my notes, look over my sort of mind map of the problem. What do you think is missing? And this is a very trivial one that I found on the internet. And as with all these templates these days, they come in a variety of flavors. You have the 4 M's for manufacturing, the 8 P's for processes, and so on. But you can just go online, you can find these templates, and you can use them. And this example on, why did I end up with a bad cup of coffee? A subject dear to my own heart. But again, we've got the procedures up here. So, there was too much water in the coffee. It was too weak. Well, why? Well, quite probably there was a lack of training of the staff. There's bits in the bottom of my coffee. Well, they probably used the wrong filter. Again, it's probably training. But it could also be the materials. The sugar was wet because the packets had got down. And so you can see that you can start to take all these different elements of what makes a good cup of coffee, and then you can take a step back and go, well, okay, what can go wrong to get to that point? I did have one client a few years ago who, after I submitted the report, came back and said, "You haven't presented your results as an Ishikawa diagram, please rewrite the report." And I had to literally go through and lay the evidence out, because they clearly had a training course on this is how you do a forensic investigation. You know, you solve the problem by doing an Ishikawa diagram. Which brings me to the don't get shackled to any particular method. Don't lose sight of the fact that what you're trying to do is understand why it failed. The way you get to that conclusion isn't necessarily the most important thing. What you want to know is, why did it go bang? And is the circuit next to it likely to go bang, or the next joint likely to go bang? And what's my risk? Was it a one-off? Or do I have a big problem because I have, you know, 100 joints of the same design? Are they all at risk? Or do I just accept that was bad luck with one? So, when I teach this in a classroom, I say to students at this point, okay, imagine you're in the office, your boss comes in and says, this cable is faulted, I need you to go to site, what are you going to take with you? And they normally get all very excited about bits of test equipment and, you know, drawings and diagrams and everything. And again, you normally say, well, what about your safety equipment? Oh, yeah. These types of cable in particular can hold charge. This insulation is incredibly good. So if you switch a cable out, this will hold a voltage on it for weeks, potentially. So if you turn off on site and you don't earth it down, before you get too close and start poking, you're going to get a very nasty surprise. In some cases, you know, if it's an old oil-filled cable or it's a porcelain cable termination, there could be big, sharp pieces of porcelain lying around. So again, you just have to be careful. So safety first, always. You never see them walk into the crime scene with the body splayed out on the floor, and they don't immediately go over and start lifting the arm up or tipping the head. You know, they walk in, they walk around the crime scene, they start taking photos, they put labels down, they photo, they draw sketches, they measure things. That people want to get in, they want to get their hands in, and they want to start moving stuff. So please don't do that. It's really easy these days. Obviously, we all walk around with a camera in our pocket. The other thing we walk around with these days, which actually is really useful for people like me who may not, may get called in weeks or months after the failure, and you're trying to understand how things were laid out, take a video. Your brain is really good at reconstructing in 3D a video image. If I take a picture here of the things laid out, it's a bit hard to work out the scale and exactly where things are. If I take a video and I walk around like this, my brain can really put that back together in your mind really, very, really easily. Scale markers. If you don't have a ruler with you, use a Bic biro. Use the lens cap from your camera. Put a business card. Anything that's going to give me an idea of whether what I'm looking at is that big or that big. Because if I just got a photo and I don't have a scale, I have no clue. Take copious notes. So the other joyous thing with cables, here's a cable. Should it be that way up, or that way up, or that way up?
Doesn't matter.
It certainly can matter. It can really matter. So at least mark the top of the cable, because in some cases, I don't know exactly if it's an oil-filled cable, or some of these come with corrugated jackets, the cable will settle inside. You can get a gap, which in the case of somewhere I was in Asia last week is a very big problem they have. Label which end, because again, should the cable be that way round or that way round? Which end was connected to substation A? That end of that end. Because when I look at it, I have no clue. Again, in most cases it makes no difference. In some cases it does. So just be prudent. It doesn't hurt to label it. Because if you don't label it, the information is gone. If you do label it, it's not relevant, it doesn't matter. When I cut things up, and it doesn't matter whether I really label it ABC or A prime, B prime, or 1, 2, 3, 4. But every time we cut something, we will label it so that we can put the jigsaw back together if we need to. I was involved many years ago with a project, and subsea cable, and it had to do with the subsea cable joints, and we had a problem. They x-rayed the joints, and we thought we had contamination that had been introduced in the jointing process. You could see it in the x-rays. And so we were at the factory, they had tables like this laid out, cutting the cable up and systematically looking at pieces and inspecting. And we finished for the day, and everything was laid out. And we went home, we went to the hotel that night, we came back the next morning, the table was clear. And according to the cable manufacturer, the cleaner had come in overnight and tidied up. All the pieces of cable that looked like this, all identical, were in a skip, with hundreds of other pieces of cable that all looked identical. That was the end of the investigation. Because they hadn't labelled it. If they'd at least used a white marker or done something, we could have found the pieces. Well, we wouldn't. We would have made the cable maker go through the skip and find all the pieces. But the evidence was gone. Boom. End of investigation. Very convenient. I didn't say that. You said that. But no. But even in the office, even if you have small pieces, it's easy for to knock something when you're moving, or you cough and small bits, get moved around. So yeah, again, it doesn't hurt to label it. You don't lose anything from labeling it. And sometimes you do need to go back and kind of put it back together again, because you get so far through the process, and it triggers a thought, could it have been this? And so then you go back and you check. So what kind of things are we using? I said to you earlier, if you come down and you feel this, I can tell that's PVC and that's polyethylene, just because of the way it feels. That's experience. Now, I wouldn't put that in a report, the Simon Sutton calibrated finger test, but it gives me information. If I were on site and the specification for the cable said this had a polyethylene jacket, and I felt it and went, no, that's wrong, I'm then immediately suspicious about everything else. I can go away and get this chemically analysed to prove that it's PVC, but I can tell just from what the touch what it is, or what it's not. Sometimes if there's been tracking, flash over, partial discharge, turning it in the light, you'll see the change in reflectance, and you'll see a lot more detail. If you try and put it under a microscope, it's really hard to find sometimes. But just by twisting and turning it in daylight or under an artificial light like that, you'll spot things. Smell, maybe not quite so much. There was a case a few years ago where some of the evidence was we opened the cable termination, I could smell burning. What he actually meant was I could smell partial discharge and arcing, you could smell acetylene. And that was in one that hadn't failed, but the fact that he said he smelt it told us that something was suspicious with that one as well, so we investigated. If we need to look in more detail, we can use different types of microscopes, simple optical microscopes, even a magnifying glass. Even quite surprising now, the macro lenses on these kind of phones are really good. Before I changed my phone a few months ago, I used to have a screw-on macro for my old iPhone. Very hard to get it to focus, but then again, it doesn't matter with an iPhone because you just sit there and you can let your hand shake, and one of the 50 photos you take will be in sharp focus. We'll use electron microscopes in the case study in a minute. And X-rays, we'll look at X-ray imaging. X-rays can be quite useful on occasions. And then if we want to identify things, we've got things we don't know what they are. If they're metals, then we can do things in the electron microscope to identify the elements. We'll look at that as part of the case study. We can use a thing called XRF. And you can even get, these days, an XRF gun. It looks a little bit like a pistol, chunky pistol. And if I was to put it on that metal, in seconds it would tell me it was copper. It would also probably tell me what, okay, this is going to be pure copper, but if it was an alloy, it would give me the breakdown of what the different elements in that was in seconds. And I can take that to site with me. And if it's an organic material, a plastic, a grease, an oil, then we're going to use some kind of spectroscopy usually. Infrared spectroscopy, UVs, gas chromatography, mass spec. And these will tell you what the molecules are. So again, if you have an unknown contaminant, not so much with cables, but in the case of transformers, there's been issues in the past where people have used the wrong grease. It attacks the seals. But you then need to prove which is wrong. Is it the wrong seal that's been used or the wrong grease that's been used? Sometimes people have put the wrong oil into transformers or into a cable termination in one case from I was involved in. So again, being able to identify it and prove it is valuable. And then of course, on some occasions, it's actually just down to the fact that it was manufactured badly. The dimensions are wrong. In principle, the conductor is meant to be absolutely in the center of this. And it's meant to be perfectly round, concentric. The reality, of course, it never is absolutely perfect. And there are tests in international standards for measuring these things. And sometimes you need to go back and repeat these tests to prove that the cable didn't actually meet the manufacturing specification in the first place. That's always a good start. Get the cable maker on the back foot. I should say, is there anybody who works for a cable manufacturer in the room? Nobody's going to confess it now, are they? And I put this in, this is more for, again, when I'm sort of teaching some of this. Because again, I gave the example where the client wanted it in a particular format, and if they tell you that up front, then you can compare everything. But I see a lot of what I would class as bad reports, which just have a lot of photos, and then they say, and this is why it failed. There's no explanation. It'll say, figure 5, shows this. And I look at it and think, well, there's no arrows, there's no circles, there's nothing to highlight which bit of this figure they're talking about. I always list every document I receive, because sometimes people come back to you years later, and it's a lot easier to have a report and go, well, this is everything you supplied, now you're giving me new evidence. You didn't give me that before. So my conclusions may change because I didn't have the full picture. So list of what happened, where did it happen, when did it happen, what did they share, good photos labelled, a description of what you did, what you found, and then some kind of dialogue about how you put the puzzle together, accepting that you don't necessarily have all the jigsaw pieces, and how you got to your conclusions. So the case study is going to sort of step through and explain some of those things that we've just talked about. So it's a 34.5 kV cable, came from a petrochemical plant in the Middle East. There was 2 circuits. They'd only been in service for about 4 years, and they started having failures. Now, most people, if they have one failure in a joint, they just consider themselves unlucky. It's probably joint or error. You repair it and you move on. You have another one not too long afterwards, you start to get a little bit jumpy at that point. And by the time you've had the third one, you know, the alarm bells are ringing, directors are on the phone, and you know, people are getting very excited. So they had 2 joint failures in a short period. There was another one that happened whilst we were talking about the project, and a 4th one by the time I'd actually finished the project. And sometimes, you know, and this happens more with industrial clients than utility clients, they don't ever seem to have any paperwork. So this had only been installed 4 years before, but they had no information on what the cable was, what the design was supposed to be, no information on what the joints were. So you're starting, you know, the first problem is you don't even know what you're looking at. So they very kindly sent me two cables. So they sent me one that had faulted, and one of these, so this is about 3 meters long in the box. About this big a diameter. And one of these chunks of cable, these are 3-core cables with a joint in. One's a good one that they've cut out as an example, and one's the one that's got the fault in. So on the grounds we had no idea what we were going to find inside, the decision was, well, we'll start by taking the good one apart, because if we mess it up, it doesn't really matter because it's the good one. We can afford to use that as a trial to discover what's inside. We know what should be there, but we're not 100% sure. So you can see there, in some ways, it doesn't look so dissimilar from this. Cables will be a little bit smaller, lower voltage, although not that much actually. Rather than having this plastic packing, this is filled with sort of like a fibrous material. And ironically, in some parts of the world, even though it's a cable on a petrochemical site, there's very little chance of somebody digging into it in theory, they still put armouring on the outside to give it an extra level of protection. So, thinking back to how they make the joints earlier, so the 3-core cable, so in each one of these big cables there's 3 smaller cables. You're going to joint each individual phase to the one on the other side. You're going to put some protection, wire mesh for continuity over the joint. You've got a braid to carry fault current, so there's like a big thick metal ribbon to carry any fault current. And then you have some kind of protection on the outside to keep moisture and contamination and everything else out. That's the order in which you would, of course, make the joint if you were doing it in the field. Of course, I'm starting with a fully made joint and I'm going the opposite way around. So I'm starting at the top and then breaking my way in through all these layers to ultimately reach the joints. So here are the 3 joints. They're sort of stacked in a triangle pattern, again like this. You can see two of the 3. One of them's kind of hidden out of sight. Like I say, the idea was to start with a healthy one, great. Use that to understand what went wrong or how it was put together. Then look at the faulted one and use the learning from the first one to solve the mystery. So this is a little bit messy. This is as we were breaking in. Don't worry about that. The key thing to remember are these 2 bits in white. So the wire mesh, which was wrapped around all 3 joints, and the fault braid, this thicker ribbon that carries, you know, the fault current, which could probably be about 50,000 amps, medium voltage cable, you know, something around that, if the cable faults. So remember these 2 bits because they are relevant to the mystery. So here's our 3 joints. As I said, we started with the healthy one. Note the fact there is a scale bar in the picture. and the little bits of electrical insulation tape around each end of the cable for labelling. So we didn't really know very much information, so we arbitrarily numbered the phases 1, 2, 3. And then we had, H for healthy, and then end A and end B, just arbitrary to keep the orientation as we took the cable apart. So arbitrary labelling because we didn't have any other information. Unfortunately, this is the healthy cable, or the healthy cable as it was labelled when it was shipped to me. As you will notice, the healthy cable has a great big fault hole in it. The client had mislabeled the cable before he shipped it. So we were very lucky that we didn't basically destroy the cable in the process of taking it apart. That was more good fortune than anything else. These things happen. So what do we do? So we started with like a visual examination as we went along. We x-rayed the joints before we took them to pieces. There's lots of subtly different designs of particularly medium voltage joints. And so it's always useful to know what's going to be inside when you don't have any documentation before you start. Then we're going to dissect it, look inside, try to find the problem, use some optical microscopes to take some good pictures, and then ultimately we're going to get into an electron microscope for some more detailed analysis, and also some elemental analysis to try and identify some of the things we found. Systematic, step by step by step. X-ray imaging. There's a company that's not too far from Guildford where I'm based. It's a non-destructive testing company, industrial X-ray. It's useful because I can put the things in the back of the car, drive them to the site, we can do the X-ray whilst I'm there, I can look at the images, and we can adjust the exposure times or the intensity of the X-rays to get good contrast. The first job I took there, it was a welded conductor, and because they're used to X-raying parts for military submarines and F1 cars, etc., they're used to looking at metals. So the guy told me that the weld in the conductor was porous. But now I'm not interested in the weld in the conductor. I'm actually more interested in the plastic bits on the outside. It's the same when you have an X-ray on your body. Most of the time you don't see the soft tissues. They're looking at the bone, which is denser. And in the cable, he just assumed I wanted to look at the conductor, the dense bit. So he ramped up the X-ray intensity to be able to image the metal. And then I lost all the soft material, all the plastic stuff around the outside. So what you're looking at in this image is the 3 phases, 1, 2, 3. The wider bit in the middle is this crimped connector that joins the 2 conductors together. So we haven't got quite the whole joint in the image, but we got the central part, and the little bit inside the circle is the fault path. These X-rays are phenomenal. So the next image is just a blow-up of that previous one. These joints are about this big, and we're now blowing into something a little bit like insulation tape, but stretchy and something. You can see in here the air gaps between the layers of tape, so it's not quite perfect. Again, resolution is absolutely unbelievable. But then we also looked like we had another developing fault in one of the other joints. I can see it. Again, because I know the orientation, because the guy was very careful, we did each joint, we did each cable 3 times, 120 degrees apart. Because if I'm X-raying that way, anything on this side of the conductor you won't see. So you do everything normally 3 times, so you get full visibility. So we knew the orientation. So when we cut the thing later, I could avoid damaging this because I knew where it was in the joint. So we laid the joints out. What I'm going to do is basically cut it at 12 o'clock and 6 o'clock. It's a tube. So it starts off with a tube, and I'm going to end up basically clamshelling it, opening it up. So I've now got two hemispherical tubes. Hemispherical tubes. And so this is what you're seeing here. So on the left is the cable. You can see the insulation, the white part, top and bottom. The conductor connector is inside this taped area. And then the two bits on the right are the joint, which has been cut in half and then opened up. There are these various strange little brownish yellow marks, which we didn't actually end up analysing, but I'm pretty convinced they're down to partial discharge activity. A lot of grease. And if we go back to those little contaminants we could see, there were wires, little bits of wire embedded in this tape layer right next to the fault path. So these are the tapes. That's these black and white tapes here. They look sooty because, again, when you get the fault, a lot of energy generated, it carbonizes all sorts of stuff. But the fact you can see them stuck into the tape layers means they didn't fall in after the fault. They're embedded in those layers of tape. So they've been there since the joint was made. I should also say that all these pictures I'm showing you now are the way that these are taken straight out of the report that went to the client. So everything I was saying about drawing circles around things, labeling things, I hope it's fairly clear that this picture came from that place over there. These pictures are related to that fault path back there. This is what I mean by well-documented photos, annotated, that go into the report. So we can see their little wires. We don't know where they've come from. They've obviously been there since the outset. And jointing is a very manual process. So it could well have just been transferred from his hands. Either he didn't wear gloves, or he did wear gloves and he didn't change them before he did this process. Rookie mistake. You would hope. But remember, they've had 4 failures by this point. So we decided to try and work out where the wires came from. So we extracted these little wires. They're about the thickness of a hair, 100 microns, turns out. So we took one of the recovered ones. This is the picture from the electron microscope. You can see it's got sort of a crust on it. This is carbon from the fault. Again, just carbon powder being deposited onto the wire. We can measure the width, 104 microns. We can work out the elemental composition. It's tinned copper, not unsurprising. But then we can take one from the wire mesh sleeve that I mentioned earlier that goes over the 3 joints. This one's almost 105 microns, suspiciously similar in diameter. Also tinned copper wire. But then if we look at the wires in the Earth continuity braid, because that's going to carry more current, they're thicker, they're 155 microns. Also tinned copper, so elementally the same, but just because of the difference in the thickness, I'm pretty convinced that the wires that were found embedded came from the mesh sleeve back. And that also makes sense. The Earth continuity braid is pretty robust. It's woven as a braid, whereas the mesh bag is quite delicate and you're trying to pull it over the 3 joints to fix it. It's far more likely that you're going to break little pieces and get them onto your hands. So it's a hypothesis. I can't prove it, but all the pieces kind of line up to make a coherent story. So let's go through our 5 whys analysis. Why did it break down to Earth? Well, there were contaminants on the tape. We found the contaminants. Why were they contaminants? Well, they probably came off the hands of the jointer. Why did they come up? Why did he do that? Well, probably he didn't have poor training, no training, or maybe lack of supervision when he was on site. Wouldn't be the first time these things have happened. And why wasn't he possibly trained properly? Well, there was probably a poor specification that said, jointers must have 5 years experience, must have done X number of this type of joint in the last so many years. So you can push some of the blame back onto the client in a way that or they didn't have a witness on site. But again, so we go through our 5 whys. Success. Everybody agree with success? Well, obviously, this isn't going to be the answer because I wouldn't be standing here. It would be a really boring case study, wouldn't it? Remember, there was this other potential developing fault that we saw in the X-rays because we bothered to do the X-rays. And we can see that there were air gaps up here, down here. Silicon rubber is really quite strong if it's in compression. If you pull it, it's actually very weak. If you pull it and just nick the surface, it will tear very, very easily. When we looked on the inside of those joint tubes, we found lots of cracks penetrating into the surface of the joint on the inside. And so the next picture, so this is now a cross section through that tube. So I've cut vertically into this crack up here and exposed what's inside. This is a tear surface. You can see the cut marks on here where the knife's gone through. This is smooth. This is a tear. So you have to say, why is there a tear? The diameter of the cable effectively has a right angle step in it. So you have the diameter of the actual insulation, and then you have the diameter of the conductor connector, which is a lot less. You've effectively got a right angle here. The silicone rubber can't follow that profile. It's stretchy, but when it tries to squeeze down, it's always going to leave a small air gap in this region. We see the air gaps in the X-ray images. And what you end up with is a profile that looks a bit like a dog bone. It's narrow in the middle, wider at the ends. Whereas what it should look like is that. It should be fatter in the middle and narrower at the ends. So I had a big argument with the client because I said that they've used the wrong size conductor connectors. It should be fatter in the middle, not thin. You can come up with explanations. Either they were trying to do it on the cheap, because normally when they buy a joint, they buy a joint kit. Everything comes in a box. The joint, the grease, the connectors, the rags, everything they need. And there are people who will try and save a few pennies and buy all the bits individually. And the client said, no, it's always like this. What he's done is he hasn't used enough layers of tape to build up the diameter in the middle so that it matches. Okay, we're both equally right in that sense. But of course, the more time they put layers of tape on, the more chance there is them introducing contaminants or messing the process. It's a hand process. We have to agree to disagree on that one. To me, it makes a lot more sense just to use a bigger connector, and then the problem never even exists in the first place. So, the reason they were having multiple joint failures was every single joint that they installed had this problem. Every single joint had air gaps, was getting partial discharge, was causing every joint body we looked at had tears on the inside of the joint tube. We only found one that had the little wires in. That was, I think, a coincidence. I didn't get to see any other joints from this client. But to my mind, the only option they have is to rip every single joint out and replace it. Because they all have this problem. And as I said, they had 4 failures in total by the time I finished the project. This is an industrial site. They lose power, they lose production. They lose production, they lose big money. For the utility, they always have redundancy in their networks. It's inconvenient, but they always can generally keep the lights on. So with that, I will finish. I hope it's an interesting case study. I like it because I think that, it proves very nicely that if you don't think about what's going on, you can get led down the wrong alley. The 5 whys takes you to the wrong conclusion if you don't think critically. So with that, thank you very much.